Welcome to homework help for the heat of fusion, heat of vaporization homework. Basically what you're going to have to learn to do is deal with graphs like this. They're called heating curves, or sometimes they're cooling curves depending on which way it's going. And generally the graph will have a description above it telling you that how many grams of material are being dealt with here. In this case it's 25 gram sample. It's very unusual for it to be a 1 gram sample. These graphs always look the same. Basically you have a lower plateau, and then it climbs, and you have an upper plateau, and then basically there are 3 sloped areas and 2 plateaus. And in every case, the lower plateau is where it is a solid, the middle plateau is where it is a liquid, and the upper plateau is where it is a gas. So let's just try to answer these questions then. Alright, so the first question we have here is Samsonol a solid, liquid, or gas at 60, sorry, it didn't come out quite right, 60 degrees Celsius. So what we want to do is we're going to go 0, and this is 40, so we must be counted by 20s. 20, 40, 60, 80. So here's 60, so we're just going to go across to here, and we see, well, it's a liquid there. Alright. At what temperature does Samsonol boil? If you recall, boiling is a transition between liquid state and gas state. And so at this temperature right here, it is transitioning between liquid and gas. So I simply have to see what is this temperature. The temperature is 80 degrees Celsius. Is the temperature which it boils. Question number 3 says, what kind of energy, kinetic or potential, is being gained by the atoms in the sample between points A and B? Now, temperature is a measure of the speed or kinetic energy of the atoms. And between here and here, although they're gaining lots of energy, in fact they're gaining 100 to 300 calories of energy, they're not going any faster. Therefore, what they're gaining is potential energy. So I'll just go ahead and circle that. Moving right along, number 4 says, how many calories of energy are needed to change a sample from a solid at the melting point to a liquid at the melting point? So here it is a solid, here it's a liquid, here it is a solid at the melting point, here it is a liquid at the melting point. So basically we're talking about between points A and B. And between points A, where it's a solid at the melting point, it gained 100 to 300 calories worth of energy were needed. 300 calories. Now, keeping in mind that this is a 25 gram sample, what is the heat of fusion? Well, the heat of fusion is going to be, in this case, 300 calories divided by the 25 grams of sample. And what that will tell me is it takes 12 calories per gram to melt this. So for the way you interpret this is, for every gram of Samsonol that you want to melt, once you get it to the melting point, you will have to add 12 calories for every single gram of it that you want to melt. That's what the heat of fusion is. What is the heat of vaporization of Samsonol? Well, what I have to do is figure out how much energy. You know what? Let me move this up a little bit. Okay, I guess I can move it that far. So basically, the heat of vaporization is how many calories per gram it takes to get from a liquid at the boiling point to a gas at the boiling point. Now, between here, where it's a liquid, and here, where it's a gas, is 150 calories. So I'm going to say 150 calories divided by 25 grams of sample. I should have written that calories. And that means we have 6.0 calories per gram would be the heat of vaporization of Samsonol. Okay, now let's look at this next one. Let's give ourselves some room here. Now we're no longer talking about the graph up above. What we're talking about is this. Water has a heat of fusion of 80 calories per gram and a heat of vaporization of 540 calories per gram. So let's look at number 7. A sample of liquid water has a mass of 56 grams and it's at a temperature of 0, but notice it is a liquid. So what we have is a liquid at the melting point, and I have 56 grams of it. It takes 80 calories that have to be removed for every gram of it I want to turn into a crystal. So how many calories would it take to remove in order to get the entire sample to freeze? Well, what I would do then is I would simply say 56 grams of it times, it takes 80 calories per gram. Now you'll notice the grams cancel out, leaving me with calories. So what that gives me is 4,480 calories, which, since there's two significant figures, I really should round that to 4,500 calories. Now, but if only this many calories were removed instead of this many, how many grams of ice would I get? Well, in this case, what I need to do is I just need to say I have 1,760 calories. And what I could say is, you know what, I'm going to do this as a conversion factor. I'm just going to say, well, 80 calories goes down below, and 1 gram goes up above. Therefore, I'm dividing. And when I divide, now again, what happens is the calories go bye-bye, leaving me with grams. And what that tells you then is I have 22 grams of ice crystals that form. All right, let's take a look at number 8. It's a little bit tricky. I'm told I have 34 grams of liquid water at the boiling point, and what I want is how many grams would boil away if this many calories were added. Well, it turns out it doesn't matter how many grams I have to begin with. Since it's already at the boiling point, any energy added to it is simply going to be used for the heat of vaporization. So for every 540 calories I add to it, 1 gram of water is going to boil away. So to do this, all I have to do is say 3,672 calories, and say I don't want calories, they go in the basement. I want grams, I'm going to put them up above. And it takes 500, if you notice, 540 calories per gram. So that means 540 calories to each gram. And let's just see what that gets me. Hang on, I'm going to talk while I turn on my calculator and say 3,672 divided by 540 at 6.8 grams of water are going to boil away. All right, let's give ourselves a little bit of room and try number 9 here. All right, what we have here is 125 grams of water. It's at 25 degrees. I'm going to add 5.5 grams of ice to it. And what I want to know is what is going to happen to the temperature of this water in the process of melting the ice. So the first thing I do is figure out how much energy is going to be extracted from the water. And the way I'm going to do that is I'm going to keep in mind that the heat of fusion, since we're talking about melting a crystal, is 80 calories per gram. So I'm going to say I have 5.5 grams of it. So what I'm going to do is I'm going to say 5.5 grams of ice. I don't want grams, so I put them in the basement. I want calories, so I'm going to put them up above. 1 gram requires 80 calories to melt it, and that gives me 440 calories of water are going to have to leave the water in order to melt it. So this much water is going to lose this many calories in order to melt this much ice. And since energy is leaving this water to melt the ice, this temperature is going to have to go down. Now I'm just going to use the heat equation. I'm going to go like this. I'm going to say, now if you remember, the heat equation is, it's delta Q equals M times delta T times Cp. Well, the Cp of water is 1, so I can ignore that. The delta Q I know is 440 calories. The mass of the water sample I see from up here is 125 grams. And what I want to find then is what is the delta T. So I simply have to divide both sides by 125. And when I do that, what I find is that the delta T in this case is equal to 3.52 degrees Celsius, and that's being taken away from the starting temperature of 25. So next time we do this, I'm going to say 25 minus 3.52 is going to give me 21.48 8 degrees Celsius.